Sulfur is oxidized to sulfuric acid. Phosphorus is oxidized to phosphoric acid. The dilute HNO3 with the dilute HNO3 copper and zinc plus HNO, they will be giving salt, copper nitrate, and zinc nitrate. Plus N, 2N. Here it is N2 plus X. This is with dilute. Next, we are moving for that test for nitrates. Test for nitrate is, one for the test for nitrate is brown rinse. Brown rinse. Brown ring test a nitrate is there and freshly prepared FeSO4 solution. In presence of acids, that is H plus. What has happened? NO, we get nitrosyl ligand. We get nitrosyl. NO plus Fe3 plus H2. And FeH2O6 times H2O6 times, this is the coordination compound. FeH2O6 times 2 plus will be taking that NO to form FeH2O coordination number should not change. This is 5 versus N. This is neutral, so this is 2 plus 1. So here, on H2O, this is brown ring. This is brown ring. What we see at the junction of these two mixtures. HNO3 is used to make fertilizers. Then NH4NO3, ammonium nitrate. Then this is used to make TNT, trinitrotoluene. That is an explosive TNT, then rocket fuels. Next, halides of phosphorus. Next is phosphorus. That is compounds of phosphorus. Phosphine is not there. Then halides of phosphorus is not there. Then oxo acids of phosphorus, not there. It's written in bracket, elementary ideas only. So we are moving to the structure of oxo acids of phosphorus. Oxo acids of phosphorus. Hypophosphorus acid. orthophosphorus acids and pyrophosphorus. Ortho. This is us. This is us. This is ick. This is ick phosphoric. This is ick. So hypophosphorus acid, that is P, double bond group, H, H. One more H is replaced by OH, P, double bond group, H. Orthophosphoric acid will be double bond group. Pyrrole is that will be POP liquids. This is OH. OH. The third of hydrogen is replaced by OH. Now from here, two molecules of this orthophosphorus acid. From that we get pyrrole, this is POP liquid, one molecule of water removed, and you are getting. So from here, and from here, one molecule of water, and this is H. This is OH. Pyrrole is POP, it's from like that, from here. From here, we will be getting pyrophosphoric acid, that is P, double bond O. Double bond O, POP, and here OH. OH. And here, PP. There it is POP liquid, same thing, that is P. OH. And here OH. So here only food. So this one can be broken, this one can be broken, can be used as a good reducing agent. H is available from there, so it is a good reducing agent. This is also reducing agent because there is pH bonds. pH bond is broken and H can be available, but POH bond cannot be broken. POH bond cannot be broken. pH bond is not ionizable, but POH is ionizable, means H can be taken as H plus. So we say the basicity of this phosphoric acid is 3 here. Basicity of this is 3 here. Basicity of this is 2 here. So basicity is decided by this OH, ionizable OH bonds. So we are finishing this 15th group. Now I'll move to 18th group, which is remaining. Group 18. Group 18 is noble gases. Helium, neon, argon, krypton, xenon, radon. Helium, neon, argon, and radon is radioactive, so its study is difficult. So we will not be learning radon. Radon is obtained from radium by the removal of one atom particles. One atom particles. So this is 226. So radon is 222. One level. Right? This is 88 2 bonds. So here. So we will not study about radon. Noble gases, they are unreactive. We know noble gases are unreactive. Noble gases, why are they called noble gases? Because they do not mingle with or interact with others. The reasons are, one is completely valence shell. Means octet is complete. In the case of helium, duplet is complete. So completely, number one reason that is completely filled valence shell and high ionization enthalpy. To take out one electron from the outermost shell, you have to supply very high amount of energy. And positive electron gain enthalpy. If you want to put one electron, that is also not possible. If you want to put one electron, means you have to supply energy. That is positive electron gain enthalpy. These noble gases are monoatomic. Of course, they are having 8 electrons. Octet is complete in their valence cells. So they don't have to combine with other atoms. So they are monoatomic. And boiling point is very less because there is no interatomic interactions. Boiling point is very less. Already 8 electrons octet complete means they do not mingle with other atoms. So their boiling points, for example, if you take helium gas, one helium atom does not mingle with other helium atom. They are individually, separately, discrete. They are standing separate. So their boiling point is very high. They can easily come out. Boiling point of helium is the lowest among these, that is 4.2 Kelvin. So since its boiling point is very low, this can be used for doing experiments at very low temperatures. Noble gases have very low boiling point. Why? Because there is no interaction between the atoms of their own kind. Now, we said they will not react with other elements, they do not interact with other elements. Still, there are compounds of Xe, xenon. Xenon makes compounds. Neil Bartlett, a scientist, Neil Bartlett prepared one compound, first O2 plus PTF6. O2 plus PTF6 minus. Like this one compound. O2 plus PTF6. This is molecular oxygen say one electron is removed. Molecular oxygen say one electron is released. So PTF6 minus. So he was able to prepare such a compound, and he thought molecular oxygen's ionization enthalpy is 1175 kilojoules per mole. 1175 kilojoules and X is 1170 kilojoules per mole. So he thought if molecular oxygen can make compounds like this, why not X? If molecular oxygen can make, this is 1175 kilojoules per mole, molecular oxygen. If molecular oxygen can make compounds like this, why can't Xe? And he was successful in making many compounds of Xe. And he made Xe plus, instead of this O2 plus, he made Xe plus. Later he made many compounds of Xe. The compounds that you have to learn are the main 3 compounds, that is XeF2, XeF4 and Xe. XeF2, XeF4, XeF6. These are the main from fluorides. Then XeO3, XeOF4. This is oxyfluorides. This is called oxyfluorides. Then XeO2F. This is again oxy. These are the compounds that you have to learn. That is XeOF4 and XeO2F2. Now let's see how can we prepare this Xe. Xe plus F2 gives XeF. XeF2, that is 673 Kelvin, and Xe plus 2 F2 gives Xe, that is 873 Kelvin. then Xc plus 3F2 gives XcF4 at 570 at 570 Kelvin, 1 bar 7 bar 7 1 bar 7 bar and 70 bar 70 bar. In this XcF6 can also be prepared from XcF4. From here, XcF4 from XcF4 you can prepare XcF6 by putting the two. So you will get XcF6 plus 2. This reaction is very important. XcF4 plus O2F2 XcF6 plus O2. Now, what are the structures of these fluorides? Structures of fluorides. XcF2, 8 plus 2, 10. There are 5 pairs of electrons. 5 pairs of electrons. So, from that only 2 bond pairs and the rest are now XcF2, 8 plus 4, 12, 12, 6, 6 electrons. So 4 bond pairs. 4 bond pairs. So Xc, this is square planar. Last year also we did square planar with 2 lone pairs. While writing the structures, lone pairs should be shown. Without that, you will not be getting the mark. XcF. Now XcF6. XcF6, 8 plus 6, 14. So for octahedral 12, so 1 doctor will be residing on X. It is distorted octahedral. This will be a distorted. This will be a distorted octahedral. That means this bond will be little distorted. Then this lone pair will be roaming all around. So F, 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 F. This is distorted octahedral. So XcF2 linear. This is square planar. This is distorted octahedral. Now we are going to the oxyfluoride. These oxyfluoride. How these oxyfluorides are obtained? Xenon oxygen compounds. These are obtained from XcF4 and XcF6. So here XcF4 by hydrolysis H2, XcF4, H2, you will be getting HF, O2, Xc and Xc. Hydrolysis of XcF2 gave hydrolysis of XcF2 gives HF, O2 and X. HF, O2, X. Two XcF2 plus 2 H2O gives 4 HF, 4 HF plus O2 plus 2 X. XcF4 hydrolysis gives, this is 6, 24, and 12. 6, 12, we double it. 6, 12, this is 24, then 2, 3, 4, that is 2. Okay, so HCF4 hydrolysis gives HCO3. Now, HCF6 on hydrolysis gives again HCO2, that is this one and this one. That is HF and HCO2. But instead of this three water, that was partial hydrolysis, one water or two water. Instead of three water, I am partially doing one water and two water with HCF6. HCF6 plus one water, HCF6 plus two water. Accordingly, one water has one oxygen, so that will be that is HCOF4 and HF. Here two oxygen, two water means two oxygens, so that compound will be formed. That is HCO2F2 plus H. Now HCOF4 is square pyramidal, while this is CC. This is square pyramidal. This is square pyramidal, and this is CC. CC you don't have to learn, but this is very important. Square pyramidal. So let's see the shape of these. HCO3, double bond O, double bond O, double bond O, and there is a O. This is pyramid. HCO2F2, that is square pyramid. COF4, COF4. Double bond O. COF4, that is square pyramid. This is O, square pyramid. So this is square pyramid. So these two structures here to learn square pyramid, these are very important. HCO3 pyramidal, HCOF4, that is square pyramid. Now, what are the uses of these? Before that, let us see. What are the reactions with PF5? We are going to learn the reactions of these compounds. HCF2 plus PF5. PF5, P has got vacant d orbitals to accept electron pairs. One bond F will be taken here and this will become minus, and so this will be. So HCF plus and PF6 minus in the solid forms. HCF2. Similar is the case, for example, SBF1. SBF1. So here one bond will be going along with this. So here SBF minus and HCF plus. But if it is in the case of sodium fluoride, sodium, metal is like sodium potassium, for example, NF. M can be sodium, M can be sodium, potassium, etc. Cesium, rubidium, cesium means alkylates. So HCF2 or HCF6. So here what happens? MF will be losing that bond F, so here will be X. F7 minus, that is N plus will be formed. This is opposite, that is Xc, F7. So metals, highly active metals, that is alkali metals, the reaction will be like this. Normally these three questions will be coming in your question paper to write the product, complete the equation. Now coming to the uses. Uses, these since they are inert, they are used in many places. You know that electric bulb contains argon to give an inert atmosphere. Argon is used. Helium is non-inflammable and light gas. It is non-inflammable and light gas. So it is used in filling balloons. Then I told you helium has got very low boiling point, that is 4.2 Kelvin. So used to carry experiments at low temperature. Having low solubility in blood, it is used as a diluent in diving apparatus. Neon is used in fluorescent lamps, fluorescent bulbs for advertisement display. What do you see on this hotel, like Hotel Gayatri, like that? You see that neon fluorescent bulb to write those letters and all. Argon is to give an inert atmosphere for electric bulbs. Helium used in diving apparatus means diving apparatus. Why? Because helium is less soluble in blood. If they use nitro, then we saw Benz produced. Nitrogen solubility in blood is high. Now, one question: no chemical compound of He is known. No chemical compound of He is known. He has got complete duplet. It is stable, very small. Then Xc, you know, it has got d orbitals. The others are having d orbitals. This helium does not have that also. High ionization enthalpy. It's high ionization enthalpy and positive electron gain enthalpy. Positive electron gain enthalpy. So high ionization enthalpy, helium very small. So it's high due to its high ionization enthalpy. So all the reasons you can write. Helium's duplet is complete. Helium is very small. It has got high ionization enthalpy, absence of d orbital. So these are the in P block that 16, 17 we have already done during that May. 16, 17 we have already done in May. 15 was not there. Group 15 was not there last year. That's why I started with 16. But in new syllabus, group 15 is also there. Now let's do some questions. ICl4 minus. ICl4 minus. To which noble gas compound it is isostructural with? Isostructural with. So let's see. This is chlorine, neon, chlorine, argon, bromine, krypton, xenon, I minus means this X. Then Cl is similar to F. So this is isostructural with this isostructural with which one? XCF. Which xenon compounds? That is XCF. So I minus means you have to take it as Xc, or Br minus also isostructural, isoelectronic, isostructural. So Br minus. Br minus also you can take like this only. So with that we finish this chapter. Thank you.